Morning, good afternoon, and good evening, everyone. This is your host Rajiv Kulkarni once again coming to the Friday talk show with all of you. Good morning, good afternoon, good evening. I said is because I don't know which part of the world you are, watching this show, but I am right now in Boston, Massachusetts, in the United States. Right now it is 10 a.m. Eastern Standard Time, which is 9 a.m. Central Time. I changed the timing a little bit because I thought that 9 a.m. Central Time is much better than you know uh, 9:30 a.m. because half an hour early is always good, so that the people back in India also they can start or they can watch the show at 7:30 p.m., which is a Friday evening, which is not too bad. Okay, let's first of all, I would like to thank everyone who is supporting the channel, who is subscribing the channel, who is sharing our channel link with all of there in the electronics community and making it grow slowly and steadily, organically, I would say. And this is your host Rajiv Kulkarni, bringing every Friday a talk show on electronics manufacturing. And today's topic, you already know, the feed forward principles on the ultra high density interconnect PCBs. Basically, when we talk about interconnect, is mainly relates to the PCBs. So what it is actually, feed forward principles are becoming increasingly important in ultra high density interconnect PCB layouts due to the growing complexity and miniaturization of electronic devices. However, they are not limited to proactive design optimization, enhanced signal integrity, reliability in high density environments, and manufacturing efficiency. So it's a very interesting topic when we talk about the electronics manufacturing and very high density circuit boards. And as you know, the electronics, the technology is growing and at a very fast pace. And we all know for the fact that because of the AI being invented and AI technology is growing, you talk about anything today, it is just the AI, right? And so today again we have Mr. Ambaprasad, the technology expert from our Silicon Valley in Bangalore in India. And Ambaprasad carries wealth of rich experience, I would say, in the design domain space, because he has been in the design area for the last 3.5 decades and above, and have worked in various capacity in different companies and also on the design side. And Amba will be presenting some slides, and Mr. Amba Prasad will present some slides and he will discuss about that. And if you please have any questions, write it on the YouTube link, and we can discuss those questions with Mr. Amba Prasad. Amba Prasad, welcome to the show again. Good evening to you. I know that you prefer to be on the audio always, not with the video because of some probably disruption or network connectivity, etc. So welcome to the show, sir. How are you this evening?
Yeah, half the world calls me Amba, so no need to add
Okay,
Prasad. I mean,
okay,
that's it.
okay, okay, okay,
So
okay.
no
Half the
problem.
world, yeah. Okay, great. That is great to know.
Okay,
And
and
welcome to the
then
show. Welcome to the show
yeah,
again. And we always would love to have you here with us and discuss about various technology aspect of our topics. And you have been very instrumental in as a support to the global electronics team here. And let me just try to share the screen so that we can present your slides. Okay. Okay, I hope everybody can see the screen.
go to full screen mode. thanks.
So, ODD and role of feed forward in ultra high density integrated designs. Okay, what's the agenda we have today?
Okay. Uh, we have about 14 slides.
Okay.
Uh, we go by definition of ODD, operational design domain,
Uh-huh.
ultra high density PCB application space, ultra high density design space, a V model applied to ultra high density PCB designs. And I think we are going to stop there. Maybe in the
Okay.
coming sessions, we go for role of feed forward
Okay.
and advantages of feed forward over feedback.
Okay.
And again, why we cannot still neglect feedback mechanisms. So I'll
Okay.
just explain them.
Great.
And
Great.
summary.
Let's do
So this is
that.
going
Okay.
to be something like a 3 to 4 part session. So let's
Okay.
talk
Great.
about advanced packaging.
Yeah.
Again, this is a repeat what we showed some other sessions. So there are some high performance and high density design drivers like AI, ML, ADAS in automotive and EVs, mobile and wearables. This is little old. Then data center, another highly growing field. Then
In fact,
EVs,
data center is becoming very, very high growth
yeah.
field, actually,
So
also in the
EVs
US.
and
Yeah.
it goes on and on. So actually here we have taken two examples. One is high performance AI application and second is high frequency and microwave boards. They are generally used in ADAS and I mean even advanced warning system radars and all.
Right.
Already a couple of weeks back we saw how electronics can protect a country, you know.
Mm. Yeah.
Two,
Yeah. Yeah.
two, 2 weeks
Yeah.
back, we
Yeah.
saw the live demo.
Right. Right.
So
Right.
that's
Right.
it.
Right.
Yeah, we have been seeing, and now this time we saw very close nearer our homes. So that's it. Can you go to the next page, please? So this is what I told the product life cycle. Research and development will decide to implement a product. Then they do from the field, they do what they want. They make the specs and then they design and they go for a launch, they deploy and they transfer the market. So, and again,
Mm.
there are TRLs and MRLs which are associated with it. So then there are some technology risks has to be taken. One of the technology risk people are taking is migrating into ultra high density. That's a leap of faith actually. So okay, so go to next slide, please.
Wow.
Uh, Ultra high density is nothing new. This was being applied to ICs, what we buy, be it a microprocessor, CPU, or a GPU or XPU, as they call it now. This was happening, but this was happening at the back end of the design. Only
Mm.
OSATs were doing. But when they get into be integrated with the actual PCB, some sort of the even OSAT like design rules will apply to the PCB design rules. Actually, there is no difference between, say, a redistribution layer design rules and a PCB design rules. That's where the convergence is happening. And these are all available 2.5D packaging or 3D packaging or whatever. So that's it. It is again, as I shown earlier, it is there in data center and networking. And again, smart devices, automotive, IoT, and these are the ones who are driving. This is at a, let's say, at a IC and silicon level. Let's go to
Okay.
the next page, please. Yeah, this is, I mean, this is a repeat slide. I was showing how many packages we can pack in a space when you started from, say, 0805, and again you go to 0603, you go to 0402 and 0201, then 01005, 008, 004. It is never ending. Now this is going to land in embedded passive boards. In fact, the components are getting inside the PCB. Okay, that's where they are landing finally. Okay, next slide, please. Even some of the analog and power supply components, they are scaling, but they're not scaling as rapidly as, say, a discrete components, but still they are scaling. So from PCB design standpoint, point 0.8 spacing between the BGA bumps or even between two component leads, point 0.8 is a cutoff for a conventional mechanically drilled PCB. When we go less than point 0.8 spacing between the bumps, we have to go for ultra high density. Otherwise, there is no escape. This will be done using lasers and additive manufacturing. Next slide, please.
Okay. ODD description.
So now,
Yeah.
ODD as applied to ultra high density PCB design play field.
Yeah.
I'm there. Don't worry. I'm just
Okay.
I'm
So
checking
I
where I
thought
am. We are almost halfway through, actually, number of
yeah,
slide
yeah.
wise.
That's okay. That's okay.
So, I mean, you are telling 35 plus years of experience or something. Even CAD companies, even OEMs, when it comes to PCB design, they call only names like schematic entry, placement, routing, and release. I mean, these are
And
the
that's
four
it.
major steps. They call that
That is
way.
it.
But ODD as a term, it called as operational design domain, is primarily associated with autonomous systems. Because if you have autonomous cars, they apply ODD because the machines will do the most of the decision making,
Hmm.
particularly for automotive industry, where it defines the specific conditions, environmental, geographical, time of delay, or even latency you can take, traffic conditions. I mean, there are a lot of similarities between this automotive and the data center. Data center also will see peak and not so peak sort of traffic. Even data centers will see east, west, and north, south traffic.
Correct.
Again, now when it comes to AI and ML, there is something even which happens on the back end. So these are the traffic conditions. I mean, just giving a similarity between the automotive traffic conditions on the road and the traffic on the internet. That's what I was trying to convey.
Hmm. Hmm.
While the concept of operational design domain is a formal term used only, it can be applied to high-speed digital PCB design or ultra-high density. The same way it is for autonomous vehicles. The fundamental principle, terminology, and definition and boundaries, the performance boundaries will remain the almost same. And again, it is basically form, fit, and function. It has to perform. That's it. Form,
Okay.
fit, and function rules everything else. So even sometimes form, fit, and function will define cost of implementation or cost of not implementation, whether you have to go for ultra high density or what, or you have to stay within your boundaries. It is taken, decision is taken by them. Next slide, please. Yeah. ODD as a description is as applied to ultra high density PCB design play field. For ultra high density PCBs, application of the in term of ODD encompasses the entire set of operating conditions and performance criteria that a PCB is designed to meet, and within much its signal integrity and power integrity are guaranteed. It has to perform. There is no escape. And here is how the concept of ODD applies, or it can be adopted for ultra high density PCB design. Data rates and frequencies. This is common between high speed digital design and ultra high density. Signal integrity metrics, power distribution design. Power distribution is very, very important. I think one third of the effort in a PCB design goes to power part of it, power design part of it. And
Yes.
generally it is
Yes.
done by experts.
Correct.
And power integrity metrics, these two are interconnected. And regulatory. Finally, when the board goes for EMI, EMC, or even safety regulation, it has to pass. I think we can take a break now. We are more than halfway through.
Okay. Let me take a break, quick break here. Welcome back to the Global Electronics Friday Talk Show. This is your host Rajiv Kulkarni, once again bringing you another topic on the the effect of we talked about the feedback and feed forward, right, on the ultra high density interconnect designs, and this normally applies onto the very high density circuit boards. And we have the expert Mr. Ambaprasad, and he spoke a few of the details before the break. And every Friday we bring this show, and if you think that you want to present something, please write a topic to us, and you can write to us. It's always there displayed, the email as well as my phone number, or you can also write on the YouTube chat session itself that you are interested, and you can get in touch and so on and so forth. The idea of bringing this Friday talk show is to help the electronics community with the varieties of topics that may go into the electronics manufacturing. So let's continue our discussion with Mr. Ambaprasad, and I'm going to share the screen again. Yes, Mr. Ambaprasad, let's continue our
Next page.
discussion of where we left early.
Yeah, can you go one slide back?
One slide back. Is this the one?
Okay. Yeah.
Yeah.
Most of the audience who are watching this, or even people who worked with me or I worked with them, whatever, PCB fraternity, they are familiar with the data rates, frequency, signal integrity, power integrity. They know that.
Mm.
But there is also what is called as a sort of signal integrity, power integrity is very important. Structural integrity. Whatever you do, the PCB should not fail because of
Correct.
densification. And component should
Correct.
not fail because of densification. That's what we are going to try to cover in the next couple of slides. Go to the next slide, please. So here is how the concept of ODD applies to uHDI PCB. Environmental condition where your the PCB is installed. It can be under a hood or it can be in aerospace. Of course, aerospace is still, they are trying to get into ultra high density, but they're going to get in somewhere there. They're there. And the component interdependencies, some components are backward compatible, some buses are backward compatible, some buses are not. When we try to select them, we have to be very careful. Power distribution, which is a tough nut to crack. Power integrity, regulatory conformance, the product has to pass safety and EMI, EMC. And again, of course, after all this, we should be able to manufacture the PCB and assemble.
Assemble
If
it.
we
Yeah.
cannot manufacture and assemble, then it remains as a layout itself. It will not go further. Okay, this is very, very important.
It remains
And
as a
yeah, next.
basically it remains as a basically testing trial
Yeah, 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 yeah. That's true.
exercise. Yeah.
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 So, ODD description as applied to ultra high density PCBs. Applying ODD mindset for high speed ultra high density PCBs. Early definition clearly define all the parameters at the very project outset, ideally in a comprehensive requirement document.
Mm.
Simulation and analysis. Use sophisticated EDA tools for a pre-layout and post-layout simulation. Signal integrity, power integrity, thermal. Sometimes power integrity and thermal are co-simulated. Thermal effects on PI and PI effects on thermal. EMI, EMC. To verify that design meets ODD criteria under various worst-case scenarios. Design for margin. Incorporate
Mm.
design margins to account for manufacturing variations, component tolerances, and environmental fluctuations, ensuring performance within the ODD. Now, the point here is we have a signal integrity margins and even EMI, EMC, we have so many dBs of margins. We have noise margins. But don't go to the extreme. You have some margin, a margin within a margin, so that when the component is not assembled properly or assembled marginally, we should be able to pass.
Mm.
Sometimes it so happens design is perfect, PCB is perfect, a PCB may fail, the assembly may fail because of wrong assembly practices. Okay, because now here we are talking of microns. You know, that's why there is a problem. That we should find out what is scenario. Don't go for a respin of a PCB again. Always, try to find out why it went wrong. And again, digital twin plays a very major role here. This is where the feed forward plays an important role. When you have a
Yes.
feed forward, all your budgets and margins are preset and it is sent to downstream activities. People will be knowing that this is what we have to expect. Testing and validation goes without saying every time it is done. That is where the loop back comes. And documentation. Document it. When you document it, please try to document a duplicate. You have to remove all duplicate definitions. Duplicate budgets, duplicate definition, we have to remove. Okay, otherwise we may twice we may say, for example, we cannot meet a placement requirement. Obviously, we cannot meet a routing requirement. And no point in telling there that because of wrong placement we went. Placement is important because that is
Mm.
the one which defines your structural integrity. Okay, routing can be compromised. There is no problem. So this has to be done. And non-implementable sort of what we cannot implement, we should go and say we cannot implement in this. And sometimes designs are done for a backward compatibility. For example, we may do a backplane or something for 800 Gbps throughput, but when we do a 400 Gbps board there, 800 Gbps design rules may look like a over design. But when you replace the boards, it has to work right the first step. So this is
Mm.
very important. Go to next slide, please. Yeah, here I'm telling this is a repeat slide again. When it comes to a real ultra high density, what it means is line space is less than uh, 75 microns, and the space between two layers on a multi-layer board is less than 50 microns, and component pitch is less than say 30 microns or something like that. So when we say 30 microns or 40 microns, the copper thickness is 35 microns. And we should know where we are operating actually. Okay. So
Correct.
I told 0.8 mm is a cutoff as far as BGA ball pitch is concerned. But here we are going something like zero point 0.4, 0.35 millimeters between the bumps. That are got its own challenges. Design is very easy.
Mm.
Design is very easy. The problem is in fabrication of the PCB, which they are catching up, but assembly is very tough. You will require a clean room environment to do this kind of assemblies. You have to think like a semiconductor or a OSAT company. Otherwise, it won't work. Okay. And yeah, next slide, please. Yeah, this is an example. I'm telling state of the art. In fact, this has been done on a demonstrator board, but it will become a mainstream in maybe another 1 year. Minimum trace width 2 microns. In a readiness level 2, it is 1.5 microns. Readiness level 3, it is 1 micron and 0.5 micron. This is going to happen on a real PCB. It is not a redistribution layer I'm talking about. This may happen in a real PCB or on a particular region of a PCB. A PCB can have even conventional components as well as ultra high density in one particular location. Line space again, the same. Bump pitch, 25 micron, 15 micron, 8 micron, 2 micron. So we're almost thinking like a semiconductor company. Interlevel wire diameter, 5 micron, 3 micron, 2 micron, 1 micron. So, and then
Wow.
through substrate wire diameter, 35 micron. 35 micron is thickness of a conventional copper board. Now
Correct.
we know where we
Correct.
are. Okay.
Yes.
25 micron, 20 micron, 12 micron. Uh,
Yeah.
Layers. Of course, when you go to ultra high density, the PCBs will be roughly something like less than 10 layer or 8 layer. You cannot have a 40 layer ultra high density PCB. It is only something like 10 layer at the max. Maximum thickness 0.85 millimeter, 1.25 millimeter. And finally, they are hitting towards 1.5 millimeter, which is thickness of a conventional PCB. So again, they are going backwards. Okay. Embedded passives are going to be used in readiness level 2, capacitors and resistors. Capacitors and inductors are used in readiness level 3. And readiness level 4, capacitors, inductors, they are going to use everything. So this is already being happening. This is happening in power supply modules. But maybe since some of them are licensed or some of them are under IP, this is going to become a mainstream in another couple of years. Next slide, please. I think this is the last slide. And
Yeah.
here I'm introducing, yeah, this is
Sorry.
the last slide. Next
Yeah.
slide.
Yeah.
This is the last slide. So in development programs, especially software development, they used to have what is called as a V curve. On left side of V, you put all your requirements and then you implement it and go on the right side of the V and find out have you implemented or not. Same thing can be applied for ultra high density PCBs also. In the next session, going forward, we are going to explain how this can be applied there. And already some of your DFM packages are using this indirectly, but we are going to tell that. And yeah, I have finished 3 minutes earlier than what time allotted to me. You have
Excellent.
any special question you can ask, or I
Sure.
can say
Sure.
something. No problem. The
Yeah.
argument
Yeah.
continues. Maybe
Yes.
next week or maybe some other week. It
Yes.
depends.
Yes.
Not,
It
next
does.
week may not be possible for me, but it
It,
continues. Yeah.
it will continue for sure. And thank you very much, Mr. Amba Prasad. I would put it this way. Half of the world, even they call you Amba, but I will still say Amba Prasad here. But anyway, I think that was a great slide sharing as well as explaining. And this is feed forward mechanism in the ultra high density interconnect design, what we presented today. However, in the next week, we have another gentleman who is going to present about ESD importance in electronics manufacturing. And he is Matias Eliseda from Mexico. And the company is Estatec. So please tune on Global Electronics, timing at 9 a.m. Central Standard Time, which is 7:30 p.m. In India. And so, Amba Prasad, please say something, or you have anything before we sign off for today?
I'll say something. The entire whatever I told in 14 pages, I can tell in maybe one sentence with a few commas.
Yes,
Yesterday I was
yes.
in OFC meeting night, 2 o'clock.
Uh-huh. Uh-huh.
So they were talking of speed, speed, speed. He was telling speed is important, speed is important. And people were in the chat box, they were telling what speed? We are already in 1.6 terabyte. He told speed to implement,
Speed
speed
to
to decision
implement.
making. And
Right.
even if you don't want to implement, you have to take a fast decision. I will not implement this.
Right,
That's
right.
all feed forward and feedback is all about. Okay,
Yeah.
nice.
Yeah. Excellent. Thank you very much, Ambaprasad. And thank you all for watching the
Thank
show
you.
today. And thank you for your continued support in sharing our link and sharing with your electronics community friends as well as other industry. And we will come back again next Friday at the same time with yet another topic, and keep watching Global Electronics Friday Talk Show. This is your host Rajiv Kulkarni signing off. And wherever you are, please take care of yourself, and God bless everyone. Thank you.
Thanks.